Okay, yeah, okay, so I'm waiting for my friend to join the Zoom meeting. But first, okay, so first let's go through. Okay, there isn't really much a point in me starting the stream before my friend joins the meeting. Uh, but let me just do some setup, right? Okay, okay, so this is where we're gonna draw our diagram. Okay, so I think the best place to begin with. The best place would be to write some short piece of code that represents how I would write a web server in C. So, okay, so the best way I'm gonna ask Cursor to do it for me. So let's choose C++. Okay, actually no, let's say we do not want it in C, right? Let's say we want it in C, not C++. So because I don't want to touch all the boost stuff, right? Let's just say we're using raw sockets, doing everything manually, and yeah. Yeah, so there's a whole rabbit hole to go down here, which is this way. I'll go through more later as my friend joins, but right now we are dealing with right now we're using the the read syscall, and it's only doing it once, right? Effectively. So this only kind of accepts one connection. So if we test it out right here, hmm, uh, oh, no, no, I need a G plus seven. Okay, yeah, and it's listening for a connection. So if I do this, okay, so this works. Yeah, this works just fine. Okay, so I'm mainly gonna wait for my friend, but I guess I can kind of begin by drawing a few diagrams. Okay, so when we start this server, what we can see is that the first thing that we do is we call the socket syscall, right? So what is a socket syscall? We trace it, it creates a new socket for type in domain. So it creates this type of socket. We specify the exact domain type and protocol, and it creates something called a socket. So I'll go through what a socket is later, but basically a socket is the way we handle is the way we handle connections to the outside world, right? And we handle it as sort of like file. So when we feel free to ask any questions in the chat, by the way. But when we create a socket, it returns a file descriptor, right? This integer is the file descriptor, and this server FD is then the file descriptor that we use to communicate with the socket. So if we call things like bind, things like accept, you see they're passing in. Hi, okay, nice. Nice you're coming. Oh, yeah, you're in the Zoom. Can you hear me?
Yeah, I can hear you, but I can't see anything though. You
Oh,
might
right,
have a
right,
share screen.
of course, of course. Okay. Can you see?
Oh yeah, I can see now. I was
Okay, great.
listening in a bit. Yeah, cool, cool.
Okay, great, great. Okay, so great that you're here. So my plan is to go through the basics of how to create. I think the best place to start for kernel networking is to understand how to write a web server in C, and then from there we see what syscalls we make, and then we trace it down to the kernel, and then that's where I can go into like what the kernel actually does. Does it sound good?
Yeah, but wait, you're coding in C++, right? So like what do you mean? You mean like the C subset of C++?
Yeah, yeah. Actually, we can code it purely in C. Right now this is I use C++, but actually I've replaced all this printf and all that. I can turn it into C very easily. Yeah.
Oh, okay, I get it.
So the reason why I chose C and not C++, is that if I choose C++, then they'll probably use something like Boost, which is a layer of abstraction above the raw like syscalls, system calls that we make to the kernel. And I want to show you the raw system calls that we make. So that's why we're not using
Oh,
C++.
that's
Okay.
cool. Just now I heard you talking about a socket, right?
Yeah.
So like how do you know like this socket like is a file descriptor and not like a TCP socket or something?
Um. Okay. So TCP socket. Okay. So there's a okay. So the TCP socket in okay. So to the program over here, the TCP socket is this precisely this socket. Like you create a socket, and when TCP connections come in, you will communicate with you talk to the TCP connection via this socket.
Oh,
Yeah.
okay.
Okay, so I'll show you the flow. Okay, so the first step is I'm going to try to draw a nice diagram on the side here. And this diagram is something you can see elsewhere also. So if you search like uh TCP, sorry, let's say socket accept bind C++. Let me find a nice diagram that I can probably try to emulate. Yeah, actually this is great. This is great. So if we look at this diagram over here, uh, yeah, this diagram is great. So on the server end, right? Yeah, so I don't need to draw the diagram already, guys. Just follow here. So on the server end, what the server will do is it first call the socket syscall over here, and what that'll do is it'll create a file descriptor. So later I'll show you when I actually list the file descriptors, I can show you exactly what that means in terms of the process, in terms of
Cool.
the in yeah, I can give you a detailed view as we step through the code later as we run it. But you first create a socket, and that gives you a server file descriptor. So the next thing that you do is you set socket options. This just configures the socket to like say like um, some options like allowing the socket the address to be reused and the port to be reused. I think the details for set socket option not so important. But this basically gives you set some options yeah for the socket. The next thing is important is that when you create a socket, it's basically like you can think of it like a file. You can think of a socket like a file. Um, when you just have a file and people connect to your when clients, right, when okay, maybe if I run it, for example, if I run it, let's say I compile the web server and I run a dot out. So you see it's listening on port 8080, right? Right now, actually I think I can just do it lah. If I do ps ax grep a dot out, one thing that you'll see is that you can see the PID of this, right? You can see the PID of the a dot out process, this server.
Yeah.
And what I can do is I can cat proc the PID slash file descriptors. Yeah, and right now we see there's a few file descriptors open, right? Um, I think what I can do is I can ls-l. Yeah, okay, this is great. So what I did over here was I listed the file dis of uh okay, what I did here was I listed the file descriptors. FD stands for file descriptors for this
Yeah.
process, right? Which is the a dot out process as we see over here. This 513535 is the a dot out
Yeah.
server running up here. And we see that there's a few file descriptors. 0, 1, and 2 are always standard in, standard out, and standard error.
Yeah.
There's some additional ones here that are not very important. It's just some cursor stuff. And more importantly, we see that 3 is the socket that we created in here. So server FD right now is 3.
Oh.
So I set socket option on that server FD3 of 3. And right now, if I stop the code just right here, right? Just right after this line, if I stop the
Mm.
code right here, the socket itself is just a file that's sitting there that's doing nothing. But how do I actually um how do I actually tell the kernel that when somebody connects to uh localhost port 8080, I want it to be bound to this socket? How do I actually tell the kernel that? I I create a sock address. I create a sock address structure over here, and this address over here is this address over here has the following fields, right? It has the following. If I look at the struct, actually, I think it's the following fields. It has a port number and the internet address, right? So if you ever do something like, if you ever do code like if you ever do code like something like you run some Python server and then you dash dash dot bind 0.0.0.0, right? And some port.
Yeah.
This port over here is this s in port. So, and then
Oh.
this address over here is the thing that you bind to.
I get what you mean when you say it binds to a port, but what do you mean by binding to an internet address?
Um so okay, so the internet address, if you bind to 127.0.0.1, then actually if even if you do port forwarding and all that, no one else can query your server, no one else can reach your server. So like you often see that if you want to bind if you want to open your if you want to open your server to the entire web, right, then you bind to 0.0.0 means it accepts all incoming connections, so from all networks. So I think maybe it's best if I can try to ask the AI to explain this.
Is it like the CIDR address?
Yeah.
It's like the
So
what we call it, the sub. It's not a subnet mask, but it's like the network IP, right? Basically, that you're giving it. You're saying that under this network, right, you can accept all incoming connections that are under this like network address.
yeah, exactly.
Okay.
So I can ask the chat GPT for a better explanation. When it binds to 0.0.0, it sounds correct. It listens to all available network interfaces. So it's more of the network interface cards that's on this machine. Some machines might have multiple network interface cards, and if the traffic comes in from card A, which is like 192.168, if I bind to 127.0.0.1, then that traffic doesn't get accepted. But if I bind to 0.0.0 means I bind to all the available network interfaces. Actually, I can talk more about this later on also, about this idea
Oh.
of a IP address associated with a network interface card. Yeah. So
Wait, it's like, is there no way to generalize it? Is there only like two options? You only choose like 0.0.0 or the loopback address?
I think you can bind it to any address. You can bind it to any address you want. And it will correspond to it depends on the list of network interfaces you have. So let me see what other options are there. Give me example with a few sample network interface cards. Okay, so let's say we have in this case, let's say there are three NICs, right? One with one in if 0 is 192.168.1.10. Another one is 10.0.0.5. Another one is a loopback. Then if I bind to 0.0.0.0, then listens on all interfaces. So that means any traffic that's coming in from any of these, any traffic inbound coming through these interfaces, any of them will be routed to my web server.
Okay. I'm starting to get it. So basically, this bind is just bind to a specific interface. It's just that 0.0.0.0 is a special one that says that
Yeah,
basically applies all the network interfaces.
yeah, that's right.
Oh, okay.
Yeah, so usually in the purpose of web hosting, I just when I'm lazy, I just do 0.0.0 because there's pretty much only one card. But yeah, so that's what the bind does. And so if you ever do the dash dash host, then this is exactly what happens under the hood. It binds a socket to a address and a port. So now that tells the kernel that whatever traffic that people come in, whatever traffic that people send, let's say I do netcat localhost 8080. If I do 8081, it's not gonna reach anything, right? Because 8081 is it goes to the kernel receives the thing that says there's no socket bound to this thing. But if I do but if I do but if I do 8080, then what we'll see is that when I do 8080, it will then appear the file descriptor will have some content that the file that this program can interact with via like read syscalls and stuff. So if I do this, then we see that bug. Yeah. Okay. It turns out I have to actually send something. So if I do netcat and say hi, then then you see that the server in this case is ended, and that's because the code doesn't do in a loop. The code just does serves one request only. So yeah, so continuing from here, if we do bind, it binds the address, right? And that opens up this file descriptor essentially to the internet, to the subnet at least. Then the next thing I can do is I can do listen, and it says it starts listening for incoming connections. So that basically kind of sets this, closely speaking, it sets this server file descriptor into a kind of polling kind of listening mode. Um, yeah. So and how and so it's kind of sets it into a ready to accept new connections, right? And in order to accept a new connection, I call the accept syscall. So right now, if I just run the server like this, and it says listening, right? Right now I've hit this line of code, and we see that right now it's currently blocking. Is that a blocking syscall at accept, meaning that it's called the accept syscall, and the kernel is blocking this program because it has nothing to give back to it. It is nothing to return. And so right now it's only waiting for it's only when I make a connection that this accept syscall will finally return. So yeah, so this accept syscall usually people put in a loop. So if I ask ChatGPT to put in a loop, it's gonna wrap this chunk of code in a in a in a loop. So I'll say I think it'd be good if I can show what happens in the accept syscall, because every time you accept a new connection, it actually creates a new file descriptor. So every new TCP connection, there's a file descriptor specifically for it. So let's say I say do the accept connections in a loop until I halt the program, printing the new connections file descriptor along the way.
By the way, right, just curious, right? Like,
Mm,
when you talk about like the polling thing, right? Like,
mm,
how does it actually work? Is there like a lot of overhead when like it's listening on a pod? Like, how does
um,
it actually work under the hood?
okay, yeah, that's a good question. So we can dive into the source code later, but that's actually a hot topic where there's a whole question of if I call a blocking syscall, um, in general we don't like blocking syscalls, right? Because if we call a blocking syscall, then uh then our program cannot do any other thing. So in general, that kind of leads us into a topic of async IO, where um we ask the question of whether there's syscalls I can call that would not block, and then it can kind of allow me to uh okay, this more applies when I have many file descriptors. So if I create many connections, many file descriptors, and I'm waiting for each one of them to send, right? If I go and block on the first one, and then I go and block on the second one and block on the third one in a for loop, it's going to be very inefficient. Instead, I want something to say, I want some kind of syscall to say like, I want to block on all of them simultaneously. If any of them return, then if any of them return, then you unblock, right? And now I can kind of wait on multiple file descriptors simultaneously. So that brings us to something like epo. I can show you example of code that does that later. Yeah, and then if you go even further, there's something called IOU ring where um it's not even it doesn't even go to the kernel space anymore. Instead, it's just the kernel space and user space as a shared is a some shared view of some shared memory, and then they just read from the memory. So there isn't even any blocking syscalls anymore. Yeah. So yeah, that's a good question. I don't know if that answers your question.
Mm.
Um,
Uh,
I,
I
Actually,
guess I
what?
think I yeah went a bit on a tangent, but yeah. Wait,
Okay.
actually my question was not really whether it's blocking or not. Like, what's the overhead of it? Just now, right? Like, let's say there's one. Wait, can you scroll up? Like, there are if listen, right? This when
Mm.
this listens a syscall, right? Did you said this is blocking or non-blocking?
Listen is non-blocking. Listen doesn't actually wait for any connections. It just prepares. It kind of tells the kernel that this file descriptor is uh is going to have connections incoming. Listen just is like a config kind of thing.
Oh, but like when
It's an accept that is
oh
blocking.
then the while loop is the one that keeps polling
Yeah,
basically.
correct. That's right. Yeah,
Oh,
you see
but
that
isn't
when
there a lot
I
of like overhead? It's like it's wasting a lot of cycles. Just keep checking, like it's just keep making system calls every time.
yeah. So this is the most rudimentary, this is the simplest form. Then later I can show you some optimizations, or I can show you what happens under the hood for listen and accept.
Bro, now it feels like we're doing low level system design for the kernel.
Yeah.
Okay, sure.
Yeah.
Go ahead.
So you can see that the moment I run a dot out, right, it printed
Yeah.
server is listening immediately, even though there's no connections. And so that means that shows that listen is not stopping here, it's not halting here, right? Because it reached this line of code.
Mm.
Yeah. Okay, I don't know whether actually listen might be considered blocking, but like what I'm trying to say is that it doesn't wait for any request to come first. Like it might still be a blocking syscall, but it's still a blocking syscall in that it waits for the kernel to reply to you, but the kernel just sets some config. It doesn't like wait for some external connections, inbound connections to before it returns. Listen just returns almost immediately.
Actually, you talk about blocking and non-blocking, right? I'm
Mm.
actually quite curious, right? Because okay, my OS is not that good lah, but what can you explain to me like what actually happens, right? When let's say like a blocking syscall is issued, like when you're so I assume this is like one thread, right, of execution.
Yeah.
Then when your process, right, let's say you only is like single threaded, right? It issues a blocking syscall, right? What exactly happens?
Right, exactly. So if you have a single thread only, and that thread calls a blocking syscall, like some IO with the disk or like some network, um, then that thread will be blocked and it cannot do anything else. So usually what languages that support concurrency do is that they spin up a separate thread that is specially dedicated to just be blocked on that syscall. So that's why we have like thread pools and like um yeah, for example, what Node.js does is it has a sing it is this Node.js is like it uses libuv, um which it seems like a single threaded kind of language, but it looks like a single threaded kind of runtime, but uh at the side when it makes blocking syscalls, it will spin up a a a side thread, like it will spin out a thread aside to to handle that, to specifically wait for that blocking syscall to finish.
Oh, okay. So the thread it constantly polls for the status of like the IO operation or whatever.
Yeah,
Oh, okay.
yeah, that's
Then
right. And
yeah, you go on.
it's up to the scheduler to kind of handle that. So yeah, so it's up to the scheduler to kind of toggle between your main thread and your IO blocking threads.
Then for async IO, right? Talk about like not okay, maybe like talk about non-blocking syscalls, right?
Mm.
So like let's say it issues a non-blocking syscall, what exactly happens in like the background? So like does the thread like go to sleep for a while or like is it always in the running state?
Okay, so when you issue a non-blocking syscall,
Yeah.
it returns immediately, whether or not there's data. So if there's data, then it'll give you, if let's say there's some new, if there's data coming in, let's say there's new connection, then it will return immediately. If there's none, then it'll return immediately and it'll inform you that there's no new connections. And then it's up to your program whether you want to like continue in an infinite loop or you want to do something else a bit more useful later on. Yeah, I can show you the example for ePO later. ePO is a non, or PO or ePO is a non blocking. There's non-blocking modes. Yeah.
Wait, so a question, right? If let's say like a thread like issue some IO or something, right?
Mm,
There's non-blocking
mm.
so that will the thread ever like be like is the thread in the running state all the time? Like after it issues this like IO blocking IO, right? I'm sorry, non-blocking IO, will we still be in the running state?
Yes.
Or like it will yield its execution, right? For like another thread to take over, like assuming it's like a uni core uni processor.
Yes.
Like
It's
so where you is control over to like another thing or like the thread will always be in a running state.
it always been
Even
a running state.
it won't be in a running state. So it will like
It will. It will. If you
it
do
will-
non-blocking syscalls, it will non-blocking I/O. It will be in the running state still. It will continue.
then let's say like the IO is like read from a disk or something. So what exactly reads from the disk? Because it's not yielding it's like control of like the CPU, right?
Mm. So if it's not, it didn't you control the CPU. It just whatever the programmer put after the non-blocking I/O call, it will just
Yeah.
continue running whatever the programmer. It's up to the programmer what they want to put after that. Like maybe do other tasks or yeah.
Oh, so like it maybe like adds it to some sort of like queue or something to be processed later lah. Like after the
Yeah.
current thread has booted its execution, then after that, then the scheduler will take over and deal with like whatever it needs to be done. Correct?
Yeah. Yeah.
Oh, okay, okay.
Yeah, that's right. Yeah, great. So yeah, so if we put this back to this, if we put this in a
Yeah.
infinite loop and we compile now and then we run it, what we can see is that I can say hi from one. Okay, so this is okay, this is not a great example, is it? Let me see. Hello message send. Oh, okay, this is a bad example because it closed the server. Let me
Also, basically, what's happening is after you establish the TCP connection, you send one message, right? Then it immediately closes the TCP connection, is it?
Yeah, in that case, it was doing that. I'm not actually, it looks kind of fine. I don't know exactly
It should
why.
be
Let
the
me,
thing at the bottom, right? The close the socket line of code.
no, that only closes the new socket. I'm not sure why it closed
Oh.
the server.
By the way, what is running? I see a variable running. Like the server socket looks to be closed if like running is false.
Uh,
Oh, it's a constant. Okay. Then
oh,
hmm.
oh, stopping server. Okay, interrupt. Sorry, let me just
Okay.
what's wrong with this? Oh, I need to send it something. Okay, there we go. Okay, wait, so that wasn't very that wasn't very think I might have to put this in a I might have to put it in a multiple in a thread. Yeah, okay. I'll have to put it in a I'll handle each client in a separate thread. And that makes sense because yeah, okay, that totally makes sense. Okay, so right now what I can do is I can run it. I can I can have multiple threads. So let's say I do put this here and I split it like this. Right, so I have one guy here, get net cat, okay, and this can say hi, right?
Okay.
And then the other guy here can also say DAT, socket for descriptor 5. This guy can also open a connection, right? Yeah, so you see that now I have two clients over here, right? They are communicating with the server here, and this server is handling both of them. One of it corresponds to socket 4 and one of it corresponds to socket 5. So
Okay.
socket 4 and 5, if we look over here, okay, so let's say I stop one of them, and I do ps aux grab either out uh ls dash l55 croc 55691 fd. You see that the file descriptor that's currently open is 4, right? It's over here, it's 4. And so what I can do actually, I can say, let's say I want dash n1 this. Okay, so let's say I close this client. You see that the file descriptor 4 disappears, right? So we see that so what remember what was file descriptor 3? File descriptor 3 was the file descriptor of server FD, right? The socket that is accepting new connections.
Yeah.
And every time, and we're running, we're now when I run right now the server is running in this infinite loop and
Mm.
it's calling accept, right? So every time a new connection comes in, and every time the client connects, it goes into accepted new connection, socket file descriptor, the new
News.
socket. So this
Uh.
accept actually spins up a new file descriptor. It actually creates a new file descriptor for that new connection. Does that make sense? So
Yeah.
every
Yeah.
new client you have, right? It actually creates a new file descriptor for this program to talk to it. So now imagine this program right now is one socket for the thing that spawns new sockets, right? That's the server file descriptor. And then now the this socket, every time I call accept on this file descriptor tree, this server file descriptor, it will spawn new file descriptors, each one for each TCP, for each client that is connected to me. So if I do something like so I do this and then I do localhost 8080 and I keep on doing this, right?
Yeah.
Then right now there's actually multiple file descriptors here.
Uh.
If I go in the foreground and stop each one of them, you can see they disappear from this list of file descriptors. Does it make sense?
Yeah.
Yeah. So that's fundamentally what's happening. So I think the key takeaways over here is that socket creates a um yeah socket. So if going back to the diagram, I think we call socket to create a listening socket, set socket options and bind and listen just kind of sets the socket to be ready to accept new connections. Then whenever the client from okay, we didn't show the client side code, but client will create a socket himself and call connect on the socket. And connect will then go through so this part where the connect actually goes through the kernel and all that, this is what we're gonna deep dive. It goes through the kernel and comes out and sends through the NIC and sends to the server side. And on the server side, what it manifests as it manifests itself as an accept. An accept returns a integer, right? Accepts it says await a new connection on FD. When new connection arrives, open a new socket to communicate with it, right? Um, yeah. So uh would this accept would create a new file scripter called the new socket, each one for each client. And then right now, this multi-threaded code, it spawns a new thread called with the function handle client with the socket number here. And new client socket, for each new TCP connection, it'll do the read and send on that socket that spawned. So yeah, so
Actually, a question, right? Like this is a implement like the system calls and everything, right? This like a implementation of the TCP standard, correct? That you're trying to do.
yes, yeah, that's right.
And then like the HTTP thing, right? It's just like it's built upon TCP lah. So like fundamentally you're just, like following like the I don't know, is HTTP even a standard?
Yes, it is a standard. Yeah,
Yeah, yeah. So this one it can be anything lah, right? It can be any application layer protocol that you are sending. But
yes,
like
yes.
fundamentally what you're doing is just like we are providing a TCP connection. After that, then you are just sending information over that basically.
Yep, yep, that's right. So you see over here,
Whoa.
actually, we can see nicely over here that uh, right now this is more like a TCP client kind of thing because for all you know, we could have not send like HTTP 1.1, we could have sent it like 4.2, right? And that doesn't really make sense in terms of there's no HTTP 4.2, right? But I can send anything I want. I can send anything I want back to the client, and it's up to me and the client how we want to interpret the messages. And HTTP is just a way to say like, oh, this bunch of strings over here means that some is okay, right? It means that and this bunch of
Oh,
text is interpreted as HTML.
okay, okay.
Yeah. So yeah, so I think the most interesting thing we can okay, so there's a few when we talk about kernel data structures, there's a few when we talk about kernel networking, it's best to I think it's best to approach it from a from point of view of examining the data structures first, right? So I think the first natural data structure we may be curious about is what is socket doing over here. So
Hmm.
if I do man socket, um let me just close this one by okay. So if I do man socket, we see that it creates a socket. This socket syscall. It creates a endpoint for communication, blah blah blah, and this is a syscall, right? So we see that it's in syssocket.h, which is exactly what this one is. Yeah, so this one, and we need to pass in these bunch of parameters. So the best way we can understand it. So right now I'm actually in kernel source. This is a kernel source code tree, source tree. And the best way would be to search for uh, syscall define. Um, I think it's tree socket. Yeah. So over here, if we try to trace the C++ code, we see that socket.h is an extern, right? Which kind of tells the C++ sorry, not C++, tell the C compiler that don't worry about the implementation of this. Don't worry about the where this segment lives, right? I'll do the linking later on. And in this case, the linking refers to linking with it, I think it's linking with I think it's linking with the LD Linux probably. Basically the Linux like this external basically says that from point of perspective, from the point of view of the C code, don't worry about linking this yet. Like I'll link it later. And in this case, I think the linking is done during probably dynamic loading, probably LD Linux. And basically the way to properly trace where this goes to is this is called define tree. Tree stands for three parameters. In this case, the three parameters are family type and protocol. And we can see that this is a kernel source code under net slash socket.c. This defines as the syscall, right? This defines the socket syscall.
Actually, a question, right, is
Hmm.
wait, so the extent, right, is for the compiler, correct? Like the
Yeah,
keyword extent is for the
that's right.
compiler.
That's
So
right.
it's like compiler, like this will be loaded, this object file will be loaded in dynamically. like during the load time, correct? Then
Yeah,
so don't worry about implementation yet.
yeah, that's right.
Oh, okay.
So yeah, so that's just to that just brings us here, and we see that it calls underscore syssocket with it's basically forwarding to this function, which is this one. And what it does is it creates a socket struct, right? So this is the first data structure that this is the first struct that is kind of useful to understand. If we see exactly what it does, it creates a pointer to sock. It creates a pointer to socket, and then it calls syscall create like this with that thing, and it sets it to sock. So we see that sock will then point to this thing. So this is the syscall that we are. It's actually going to this is a code in the kernel that's actually going to create the syscall, and then after that it maps the file descriptor, right? So we can go to these two later, but let's first examine what is actually in the struct socket, because I think it's best when we look at the relevant fields of the struct socket to understand what a socket actually is. So we see that there's nice documentation here. There's a socket state, right, for whether it's a connected stream or no space. Not very important. Sorry, whether it's connected or not. The socket state is whether it's connected or not. Not very. Actually, wait. There's a command to what? Let me ask. What's the Linux command to show the status of file descriptors? Because it's kind of nice to see actually. ls off, is it? Let me try. ls. So yeah, I think this might be nice to ah this might be nice to show you
Okay.
the connection states. Let me try this. And I can do grep in the out ls of dash p61193. Yeah, okay, this is actually kind of nice.
So actually using this, you can build your own libraries for like your own like web server libraries are basically
Yeah,
like don't
exactly.
backend frameworks, right? Fundamentally, this is the building blocks of it, correct?
Yeah, exactly. Everything is just a wrapper. Okay, so this is really nice actually. Let me do this in a watch dash and one this thing. Okay, yeah, so this is really nice. So this is the list of all the this is a list of ls off. What does ls off do? It lists all the open files, right? So this goes into open files, and file descriptors are they're kind of related. That goes into more of the file system kind of in the aspect of the kernel, so I won't talk too much about that. But what I like about this specifically is that you can see the state. You can see the state that the file descriptor tree, right, is an IPv4 type of a socket, type of file descriptor. Um, and in this case, it's in a listen state. So if I'm not wrong, what I can do now is I can now do netcat, and this okay, I'm not let me see if I do. Yeah, if I do, I think if I do this tail, you can see the end. It's kind of annoying. Let me just expand this view so I can see
Oh,
more.
by the way, right, I see the type that is IPv4. So right just now I saw like the types, right? There's like the Unix socket for local communication. Then IPv4 is IPv4 equal to the INET type?
inet type.
Yeah, because you know, I saw right there were like
Yes,
several
yes,
like kinds of sockets, right? So IPv4 means it's the INET socket, correct?
yes, that's right.
Oh, wait, is it like did you specify it to be like INET or?
Um, yeah, AFINet is corresponds to
Oh, okay.
IPv4.
Okay,
Yeah.
because I was thinking, right, like currently we're just communicating like locally in the computer, right? So like technically you can just use a Unix one, right?
Yes, technically, yeah.
And does it have lower overhead? Do you know whether it has lower overhead than the iNet one?
I would imagine that actually, if I use a Unix socket and other processors are writing directly to the Unix socket, then yes, because it doesn't have to go through the network stack, right? It doesn't have to go through um yeah, I would think so actually. It'll probably have
So
lower overhead.
so right, like the iNet socket, right? Does it so it probably involves like the NIC, right? Whereas like Unix socket, I assume they don't involve the NIC.
Uh yeah, I don't think Unix socket involves a NIC. It's just a file, it's just a socket, and there's people can have file descriptors to it, and they can write to it and read from it. And that's inter-process communication without any networking. You only need a networking when you want one computer to talk to another. So you need a way of connecting them, and the way to do so is via the hardware, the NIC. And then that's when you actually need to do the binding to say like this NIC is actually corresponding to this file descriptor you send to this address.
Ah,
Yeah. So yeah, in some sense, interprocess communication is done using Unix sockets. That's one way to do it. And if you want to kind of have intercomputer communication, right, inter-device communication, then you kind of bind those sockets to IP addresses and ports, and then that's how computers communicate over a network. Does it make sense?
yeah. So it's like if like the Unix socket is used, right, it's a form of like message passing, right?
Yeah,
Like
yeah, that's right.
it, of like interprocess communication. It's not using like any shared memory. And also, by the way, right, I'm curious, this file descriptor, right? This file,
Mm.
it is it memory map or like what's the case with this file?
No, I don't think it's memory mapped. It's a file descriptor. When you do read, this is a read syscall. It's not a what memory map means is that so this read syscall actually calls the kernel to read from the file descriptor, and that goes through all the 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 the, the whole kernel code. Um, but when you say memory map, it's a different thing. So when you do memory map, what you do is that you do it just once, right? You do the memory map just once. And then after that, after you do the memory map, from the perspective of the user side code, the user land code, is just reading an address. It's as good as reading from like um a
Oh, okay, so
pointer.
it's different. Okay,
Yeah.
okay,
And then
I get it. Yeah.
the kernel will then handle if you hit a page fault and your memory there is like it says like nothing there yet, then the kernel will then handle that page fault off um transparently from mm, sorry, not transparent, opaque to the user. User is just reading a memory address and it sees, why this memory address read take a bit longer. But actually under the hood the kernel would do the page fault and then it pull in the stuff. Yeah.
So would there be any hit like or any overhead with like using the read syscall? Like will it like cause like disk seek or something?
Both of them, actually both mmap and read syscall will cause fetching from this because you still need to get the data from this. But what the read syscall is what memory map is really useful for is if let's say I do read, let's say I read like index 20, right? And then for some reason in this code I do read index 20 again and again and again and again. If my user side
Ah,
code is stupid and it doesn't
okay,
handle the caching, right? Then
yeah.
the kernel doesn't know whether it has changed or not, right? So it will just keep on doing the read syscall. But if you do memory map, it's in some sense the kernel handling the caching for you.
And another thing, right? I'm curious, right? Like, let's say when I send like so after the TCP connection's established, right? Then I send some data to the server through the TCP connection. Then right, this data, right, will it be written to disk or like I assume it's in memory first, right? It definitely must be in memory first.
It's in memory. It's in memory. When you create a socket, it doesn't live on disk. Just because it's a file descriptor, doesn't
Doesn't
mean
mean
that it's a file.
oh
Like a file
yeah,
descriptor, um, yeah, later I'll show you the file ops. You can implement file operations like read and write for it's an abstract interface that allows you to implement the handler for read and write. So the handler for read and write doesn't necessarily need to talk to the disk. Yeah. So that's what they mean when they say that everything in Linux is a file. Just because just because the 0, 1, and 2, you see, just because file descriptors 0, 1, and 2 are file descriptors doesn't mean that they actually correspond to a file. Like this dev pts sudo terminal is actually a console, right? It's actually not a file.
Oh, so like this file descriptor doesn't correspond to a file, but rather like a location in memory.
Yeah, it corresponds to this console actually. So what I can actually do is if I say I can actually do this really cool thing where I say let's say I echo hi to pipe to this, right? Sudo it. Uh, well, it's not working.
Hmm.
Okay, I don't know why it's what if I do sudo dash hi echo hi def bts9.
Sorry,
This
you say console, right? What exactly is a console?
it's actually physically this thing. Like, is this all this bunch of stuff? Well, let me ask ChatGPT for
Like is
uh
it a process or like what exactly is a console?
uh I think there will probably be okay. I think what I can say now is that a console, this dev pts is
Device.
a implementation of the file operations interface. So like you can write to this PTS and you can read from this PTS.
Oh,
Um, and the thing that handles the write and the read syscalls is in the Linux source somewhere. And what it will correspond to is it will correspond to whatever is, if you write to it, it will appear on this console. If you read from it, it reads from this console. So it's not if you want to say where does it live, yes, it lives in memory because this the struct that you allocate for that thing would actually be living in memory. Yeah.
I see.
There's a really cool experiment I can do. Oh, T. Yeah, you see. So right now, right, know that this thing is a terminal, right? This
Yeah.
thing up here. What I can do is I can echo stuff into sudo t it. I think T just kind of opens it. And you see it appears here. This output didn't come from the program, didn't come from the web server, right? This output didn't come from the web server at all, right? It came
Mm.
from this other process which was writing to this uh to this uh to this to this pseudo terminal file. Yeah. So that's what they mean when they say everything in Linux is a file. Like even stuff that are not like files, they also appear as a file. Uh yeah, I can show you the exact code if it's clearer later, but yeah, that's
Uh,
the question.
okay, thanks.
Okay, so where were we? So yeah, so it creates a socket. So as we see a socket is there's a socket state. All right, what I wanted to show you is I wanted to show
Yeah.
you netcat localhost, right? So you
Mm,
see it says accepted. If I say hi, yeah. So you see that when I say accepted, right, the file descriptor was 4, right, for the new connection. And see over
mm.
here 4, there's a new thing called established. So um that corresponds to okay, in this case the socket state actually refers to this one, the listen state. Uh yeah, but I just want to show you that this thing called established, and if I type something and do it okay before it disappears, it will actually show close.
Oh. Wait, so like when so whenever a new connection comes, right, then a new file descriptor is created to like deal with it, right? And
Yeah,
then
that's right.
show establish, correct?
Yeah, that's right.
Okay.
So there's actually a whole TCP. Actually, I'm not sure. Inject the later if I inject a bit of code, maybe I can show you exactly the process of establishing the connections in like slow-mo, low-key. Yeah. So okay, but for now, let's continue with a socket struct. So what's really interesting is that we see that a socket has a state, is a type, right? Some flags, and the most important part over here, okay, there's the two most important fields are these two. One is a file, and one is a sock. So more on sock later, right? But file, you see that struct file, what does it represent? If I zoom in a bit, it says that struct file represents a file. Yeah, it represents a file, right? So 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 this file is precisely what I mean by like,
Everything's a file.
yeah. So the socket has a pointer to a file which when you call like open on it, it will when you do certain like open and write and read, it will it will call file operations, right? So a file has a struct file. One of the most important field is file operations. As a pointer to this struct, and this struct, if you check it out, it's a whole bunch of function pointers, right? So imagine if I create a socket, right? One of it is I must
Oh,
specify a file pointer.
I get it. So it's like a function pointers. Basically, then you can implement.
Yeah,
It's like interface for you to implement like the relevant functionality lah.
yeah, exactly. So
Oh, oh.
this is what we call like C style polymorphism, because like you are in some sense the file operations over here kind of represents like an interface, right? All these are functions that you can override. Yeah, you can override. If it's null, then means that it's unimplemented. Then there's probably some check in the code that says if it's null, then you wanna like throw an error or something. So maybe if I ask ChatGPT to implement a simple like file system, you can see that it actually implements all of these, and then it registers these function pointers to point to it.
That's cool.
Yeah. So yeah, read and write are here. Read and write are here. Poll is also here. There might be a is there an accept? I think accept is in the socket. Yeah, and you see mmap is here also. So this if you write your own file system, you can specify how you want mmap to work, right? You can make mmap do whatever, make your file system respond to mmap in whatever way you want, right? It can be dumb, it can be just like return -1, or it can be really fancy, like call some hardware stuff and all that. Yeah. So I wanted to show that that's one of the things I wanted to show. Um, yeah. So before we go into syssocket create, so over here before we dive all the way in, um, okay, there's a whole bunch of stuff. But I think the most important thing. Okay, so if I step one step at a time, right? Syscall create, right? So I step forward. Now I'm in syscall create, right? And what does it call? It's called sock create. So there's always a bunch of the pattern of the kernel is always like some high level function call something, and then it goes through a bunch of functions and call function deeper and deeper and deeper. And at the baseline is almost always a function pointer. So what I mean by that is if I go syscall create, it calls socket create. If I go socket create, it calls another socket create. I go socket create. In the end, right, you see it allocates space for the socket. So this says allocate the socket and allow the family to set things up. It allocates the socket, set the type and stuff. And at the end of the day, the thing that really, really, really creates a socket, honestly, is this thing, pf create, right? Pf create, and they pass in all the parameters here. And so what is this pf over here, right? So this create, if I check it out, oh, it's a function pointer, right? It's a
Oh,
function pointer. And so what is this pf over here? This pf is protocol family, and where is this where is this pf initialized? So what we can do is we can search for pf. You can see that pf is initialized over here, right? RCU dereference. This dereference low key, this RCU is just some kind of concurrency primitive. Low key, this is just saying dereference, but like be careful with like locking and stuff. So you can for now you can imagine the if you don't care about concurrency, it's just a dereferencing, right? And what it means when I dereference the net families over here, this net families is a static read only thing. Um, for it's a static it's a static pointer. Sorry, it's a static array, right? And what is it array of? It's an array of pointers to net proto family, right? It's a protocol list. So what this net families does is it maps a number or index to a net net proto family struct, right? And what is net proto family? Once again, is this thing, right? So the whole point over here is that what I'm trying to say is that PF ultimately comes from this integer family, right? And this integer family, where does it come from? It comes from the parameter here. And so if you go back up again, you see that this parameter family, where does it come from? It comes from here, right? And this comes from here. So you go back up again, sys create. Ultimately, that's gone too far. Ultimately, this socket family thing, it comes from here. It comes from whatever the user passed it. So the whole point is that um, what the user passed in is just an integer, right? An
Yeah.
integer being the family, and this will be used to index an array of an array of um an array of
Like the protocol, the primitives thing, right?
yeah.
Like
So
uh actually, right, what is this syscall define tree like syntax? Is
oh,
it like
it's a macro.
oh, it's a macro?
Yeah. And then there's some stuff. No, I don't really know what it does, but it just defines a syscall that there's some linking that goes on under the hood, but
Okay.
I don't think it's very important to know exactly what it does. It just creates a syscall that essentially it kind of thinks you can think of it as compiling I think it's kind of like extern socket or in socket that eventually it'll be compiled into the LD Linux.
Oh,
Yeah.
okay.
So
Cool.
yeah, so that's quite cool. So when you want to define your own, let's say you want to define your own protocol family, right? This family
Yeah.
thing is a protocol family. If you want to define your own protocol family, all you need to do is let me just close this thing. Uh, all you need to do is just you want to declare your own protocol family. All you need to do is you need to write a you need to write a kernel module that implements this thing, right? You need to write a kernel module that implements these functions.
Oh.
Yeah.
But
So I
wait,
can show you.
what's a kernel
Sorry.
module?
Sorry.
What's a kernel module?
Oh, it's like a plugin. It's like a plugin that you can load after the kernel has started.
Oh, okay.
It's a great way to learn how the kernel works because you're writing parts of the kernel that you can load and unload on the fly. I can show you later. It's quite simple actually.
Cool.
Yeah. So so the key takeaway over here is that that's what a socket does, right? And that's what a socket does. And it seems intimidating that maybe if that was what a socket was only, then what about the rest, right? But in reality, the theme is all around the same. Like let's say you're curious about listen, right? So let's take a look at what listen does. So let's take a look at what listen does. For example, okay, in this case not socket define tree. In this case, if I man listen is two, right? So I do socket define two. It's here. It's in the same socket.c file. This is listen, right? So you see, noting that we pass in a file descriptor and a backlog. Most important is the file descriptor part. What the backlog is. The backlog is I don't really the oh it's the maximum length of the queue for pending. Oh, okay, more on the pending queue actually. The pending queue is kind of interesting. Yeah, but for now, the system just takes in a file descriptor, and does this, and then okay. So what we see here is that when we call listen, right? We pass in a file descriptor. It's just an integer, right? We
Mm.
want to turn this integer into a sock, right? Because um, yeah, because this integer is mapped to a socket. So
Yeah.
we create an empty a pointer to socket right now is null at this line. And then we call sock equals to sock from file, right? And then you call fd file on f. So fd file is a function that basically turn the fd file is a function that turns turns the f into a file pointer.
F was an int, right? So it turns for is it?
Yeah, it turns into a
Wait, what? What?
okay. So what we see here is that um it turns a number into a file pointer, and then it
Turns the file pointer into a socket.
yeah. So let's see what this does. So
It
if sort from file,
actually, what is
uh,
like,
sorry.
or what
Oh,
is
this
this like a
is I think it's
function?
branch prediction.
Oh, for price prediction.
Yeah.
Oh,
So you see that okay. So if I pass in a file pointer, in this case, we look at this fd file thing. It's actually just a cast. The word here, I think it does nothing very fancy. It just casts it into unsigned so that we don't have like issues with like the two's complement and all that, I think.
oh,
So I think what this okay, so usually what this will mean is that the fref is a number. Um Let me check this line what it does with the maybe explain how FE file works. Uh, Yeah, but the point is that this retrieves the socket basically. How it does so under the hood. Uh let's see what ChatGPT says. The bitwise cast to struct file. Okay, I at the moment I
no
don't
worries, no
really
worries.
know why you can cast a integer into a pointer like that. Oh, okay, might be due to virtual address kind of thing. That okay for now. Let's just say that we managed to convert it to a file, pointer to a file, right?
Okay.
And then what we do is we access the file op and we check whether it's equals to the socket file ops. So the socket file ops once again is a whole list of is a the file ops is a whole bunch of is a whole bunch of so these okay, so remember what file operations was, right? File operations
Yeah,
was
yeah.
a struct of function pointers. So this is a static thing that says that um this is the file operations for what a socket file is. So in Java terms is low in inheritance terms is low key like saying like uh a socket is a file, right?
Yeah.
And whatever thing extends the file, it can override certain file operations, right?
Ah,
And these are the implementations. These are the these are the overridden methods, right? And they're saying that the socket files have these set of file operations. Um,
oh, okay.
and what it points to, these are all function pointers, right? And these are all function pointers to For example, for read iter or for mmap, let's see read iter is this one. This is the implementation for reading from a socket file. Yeah. So these are the list of, if you click into each one of these, right, these are the list of implementations for like this or for polling for a socket file. This for writing to a socket file. Um, yeah. So that's what this struct means. And and so this is saying that if the file operations of this file is the socket file operations, then then we return private data is low key like a area where you can add additional text, like additional info. It's like a generic field that you can put any kind of thing you want. In this case, it
The
puts,
metadata.
yeah, like metadata exactly for a file. Right? Because a struct file, like you when you look at this, nowhere ever do you see like a mention of like sockets. So, but if they want to keep the implementation, if they want to keep the interface of file to be as generic as possible, then they surely need to have a place where you can have a pointer to whatever generic implementation, whatever add-ons, whatever bells and whistles you want to attach to a file.
No wonder that there's so many
Yeah.
like levels of interaction. Wait, bro, I just realized I something important to do, right? My friend just told me like a project due today. So I think I'll
Okay.
bounce first.
Sure,
Maybe
sure,
next
no worries.
time you teach me more stuff. Thanks.
Can. No worries. Thanks for appearing. Yeah.
Thanks for sharing also.
No worries, no worries. Can. Bye. Um, okay, I think I'll try to look for more friends to join the hello. Welcome, Eric. Um, yeah, okay, so I'm thinking whether I'm considering now whether I should pause the stream or whether I should uh continue talking about it. I think I'm probably gonna call it a day for today. Um, I can continue. I'm running a bit of a sore throat from speaking a lot, so I think yeah, I think I'm probably gonna rest. Yeah, and I gotta go for something soon too. So I'll probably continue this another session probably sometime this week. Yeah, so if not, thanks for tuning in. I will probably end the stream for now here. This is part one. And stay tuned for part two. Yeah. Bye.